Thank you. Yeah, so what is scalability and future-proofing? So the first one is the more important part. So my name's Sunny, and I work as an architect at ThinkCap. And this talk is really about three simple things. Just a general overview of scalability, which many, I'm sure, in the audience have sort of struggled with and fixed things and learned their lessons. And so we'll have a bit of a discussion at like a slightly high level of what it is and what are the challenges. And then how does TiDB solve some of those problems and issues? So that's roughly what it is. So this was in Max's talk earlier. The fundamental principle of scalability is the ability to expand from zero. So basically, you should be able to, everything else, the user experience, the quality of service remaining the same. The only thing that should change is the cost. Everything, you should be able to expand very quickly. And what are the things that are like good properties in a scalable system? It should be flexible, so you can scale up and scale down easily, so that you save cost when you're not using resources that you don't need. Performance should be stable. Most people like stable performance, and getting stable performance is a challenge, as everybody who's tried to do this. It should be available. In today's world, if availability is not on your radar, then I think you're doing something wrong. So available. And it should be easy to operate. So as scale changes, operations also become very challenging. So these are the sort of things that we'll talk about in this presentation. And this will set the scene for people who are going to come later and talk about more concrete things around TiDB. So as the business changes, I mean, this is obvious, the technical, you have to implement whatever the business wants. There are technical challenges, there are new features, there are more users. So if you have more users, new features, and more data, you need to scale up now. You will have more connections as your users go. That is a big challenge. You will have the frequency of requests to your system will be higher, not just the number of users. Your data could grow like exponentially sometimes. Depends on what sort of service you have. And the bigger your system, the more services you provide, your metadata changes themselves become a huge challenge. So actually, one of the things we noticed, I was at VLDB and we had this discussion, was that there hasn't been much research in large-scale schema changes from academia, actually. So those are the problems that are being solved by companies like TiDB. So what happens when you increase application users? I mean, everybody knows the number of connections increase, depending on how your application is structured. Maybe you need fast connections, you need long, slow connections. And if you have 100 million users, 200 million users, how frequently do they access the system? These are real engineering challenges. If you have 1,000 users, it's very different from 100 million users. And 1 billion it's not linear, it's almost exponential, handling the complexity around those things. So what is the impact on business? So if there's a degradation of service, it impacts your business. I mean, it's a real cost. It's not some imaginary cost. Your operational complexity also increases dramatically. Why? Multi-region. You have to think about so many things, about consistency across regions. How do you handle failover? How do you provide the same? The latency will go up if, let's say, some of the data is not located to where most of your users are. How do you think about those sort of issues? These are very serious challenges in operations. And as I mentioned, schema changes are also become a big, so let's say a create index. You have a legacy. I have seen tables of 20 terabytes, 40 terabytes. And I also know of an example, and you can look it up with the person who actually probably ran that create index for their company in one of our webinars. It ran for, I think, 3 months, if I'm not mistaken. So these are real things. These are not made up numbers. I mean, they may sound incredible, but people have experienced this. So now your data increases, then what happens? Your disk I/O may increase because your caches don't increase at the same scale. But your data on cheap storage like disks will increase because it's easier. But your caches don't increase, so it'll affect your query latency. Your now data is spread across multiple regions. What happens? Then you have latency over the network. I mean, consistency is another big problem. So now you have a distributed system. What about internode traffic? Your network costs go out. Is your system doing too much of network traffic when it shouldn't be doing network traffic? And this is now hidden from you. You think you're talking to this one endpoint, which is a database. It's not. It's like a completely different beast under the hood. Data movement. So now you want, let's say you're doing sharding, and now suddenly you've decided to reshard. You're moving data around. Now your application has to change. And now you have, one problem is how to shard and reshard the data, and now you have to go and tell your application developers that go change your application so that your data has been moved around. So any application that knows the location of its data will not scale, will cause lots of operational challenges. You want this to be automatic for you. Data reorganization will throw in the schema thing. So your data increases. Let's say you have a 200 terabyte cluster. Backup, restore. How do you test your backup at 200 terabytes? How many people here have tested a 200 terabyte backup and restore? One. It's very rare, or two. There you go. These are rare, and these are definitely companies that work at a different scale. I know where you worked. So these are very difficult things to do and test. And so you want these to be easier for you. We'll get into that a little bit at the end. So you add more nodes. Okay, I have a cluster of n nodes. Now I add, the data is going fast, so I anticipate, and I want some capacity there. And I add 5 nodes. How is the data now going to be moved around? When are those nodes going to be available for general purpose use? So there is a ramp up cost. You want that to be lower too. When you add a node, do you decide where the data is going to go on which node, or do you want that to be done for you automatically? You want it to be done automatically. Redistributed. So now certain clients are now, so when you stay, in case of, let's say, I'll take TiDB as an example. Let's say you have multiple TiDB nodes, SQL nodes, and you have certain clients connecting to a certain portion of the nodes because they happen to be in some region. Do you want the data to be closer to them to reduce latency or not? Again, more nodes means more things to manage, and everything affects everything else. Storage these days, if you're using one of those cloud things, again, it's network storage, and complexity goes up there too. So all these affect scalability, all these things. And the only thing you want that should change should be your cost, something that I mentioned earlier. So you should be able to add resources to your system, and you shouldn't have to worry about all the other. In reality, is very different, but you should worry as little as possible about the operational side of things and other side of things, the quality of service. And as Max said, you don't want to worry about the business logic, the business users, and the quality of service. You just need to worry about scaling your system. You want to have one problem. So more tangibly, as just cluster increases and workload increases, your user experience and your operational experience should not change. Does it hold? That's the question you need to ask when you're talking or thinking about scaling your system. And what are the various dimensions in that? Those were, if you remember, Max had this big slide, and I think I'll summarize it later. So duration is anything to do with time, latency, right? Does it increase? Network or query latency or whatever. What about the size of the data? Is it write amplified? Are the data on this data structures the right kind of data structures? An example would be LSM, B-tree, or something like that. What about things like consistency, like durability and all these sort of, in a distributed system, it becomes more complex. It's not the same as a single node system. What about your performance? What about availability is like in my eyes at least, an extremely important thing. And if you don't have availability, then what's the point of scaling your system to whatever it is? So these are the various dimensions, right? Volume would be anything that's measured in size, for example. Read, write throughput, data volume, query volume, latency. Latency should be probably in duration. So anyway, write queuing, I mean, all these are just the standard things that any distributed system will do to satisfy whatever service it's trying to provide. So the things that I have seen where people have struggled a bit are schema objects, like data dictionary, distributed data dictionary, and very large data dictionaries, because now as the scale grows, you could have a SaaS application. And one number that I heard like 2-3 months ago from somebody that we were having some prelim talks, they had 300,000 users, and they expected 100 tables per user. Or what is it, like 30 million? Yes. Like serious number. And these are not small numbers. These are huge numbers. And writing a system to manage that is a far more difficult problem than it looks. So yeah, backup. Backup is another very important thing. I mean, if you don't have good backups and you can't test them and you actually have no idea whether they work, it could be like a bankruptcy issue if you can't restore your system back to the way it was before whatever disaster. And Amazon has these blackouts every now and then, even though they guarantee God knows 100% or 99.x. So people do have these problems in reality. It's not as if they're just imaginary problems. So what's the ideal that everybody wants? As you keep adding nodes, everything else, your timing, query latency should be stable. In reality, it's never that perfect, but you want to be as close to perfection as possible. That's one of your goals. And the other one is your space should increase linearly. So if you're growing at, I don't know, X number of users or data, the space should be fully utilized and effectively as you add more nodes. And that's also never usually perfect, but you want to be, 70% is usually what I've heard. I could be wrong, could be 80%. So it's somewhere around there. I think nothing scales perfectly. But those should be your targets when you're talking in terms of scale. So these are the most common things that people measure. And latency, as we've gone over this, throughput should scale linearly. This is an important one. It's becoming more important as data sets grow. And it looks like a very difficult problem, but it's a difficult problem if you're using, let's say, a single node for creating an index and then distributing the changes. A good example is, let's say, like I come from a MySQL background, so I can speak from MySQL experience. So in MySQL, whether it's an Aurora flavor or it's standard MySQL cluster or whatever, let's say a create index goes to the right node, the front node. It does everything while the changes that are being sent to the other nodes are blocked. So the lag keeps increasing. And let's say you're doing 1 terabyte, just as an example, and it takes 10 hours. For 10 hours, the changes to that table to the rest of the machines in the cluster are blocked. It's a stop operation. You don't want them to stop. It's only when the DDL completes that when it's externalized on the main node is it when the changes are sent to the follow nodes. This is in Aurora is the same thing, and same as with the MySQL replication or whatever. So how would a distributed database do it? You want every resource in your system, whether it's a compute, storage, to be working on the problem. Now, what's the other complexity it adds? It can affect, if you put all the resources towards create index, for example, it will use your disk, and for sorting, it will use your CPU. It will start affecting your business transactions. You don't want that. And create index is usually not that urgent. It can be done in the background. So you want a subset of your resources to be dedicated to that do not introduce jitter or any other issue in your business transactions. So that's the model that TiDB follows, and I'll go into it a little bit later. So this is actually an interesting problem. So disaster recovery, again, you want your backups to be easy. So in the case of TiDB, to get close to this ideal, you can do multiple parallel reads on your storage nodes, and you can do the same thing with the restore. So that's how TiDB would solve that problem. Shard failover time. So you want automatic failover. You don't want to be monitoring connections and getting alerts, or this thing has gone down, let me just move this here, let me move that there. It should automatically fail over at scale. Because you cannot manage, as the number of nodes go up, some of them will fail. It's just a fact. But you want that to be automatic. You don't want somebody behind the curtain pulling the strings, running around, sleepless nights. You want that to be automatic. TiDB does that for you. Tenancy. So as you should be able to have multiple applications. So I'll skip that one. So growth is good. Everyone loves growth. I would love to have these kind of problems. My main point in this would be, beyond a point, even simple things become difficult at scale. Analyze table for your optimizer statistics. You've got 10 million tables. How do you do it? It'll bring the system down to gathering the statistics. And it does do it. So you have to have some mechanism to manage it at scale. And if you don't have the, let's say you import a table and you don't have the statistics, your query will certainly start doing, the optimizer will have weird plans. How do you do it at such a large scale? That's it. Simple things become very difficult. Backup is like a simple thing if you're dealing in 100 megabytes or gigabytes or whatever. Stable user experience, very difficult because it touches too many things. Schema change, very difficult. Historically, people have done manual sharding and resharding, and if you have done resharding frequently, it is the stuff of nightmares. It is not an easy task. Anybody who's done it probably doesn't want to do it again. Partial failure is a big problem in a distributed system. It's like a generic problem in distributed systems, and databases, it just makes it worse. Oh, sorry. Reasoning about failure is a big deal. You want a system that gives you certain guarantees that you can reason about, that you can, when you talk, when you're trying to solve problems, or you want to make some assumptions, it is easy to reason about what your system does. These days, everyone likes using TLA plus, for example. You should be able to, write something in TLA plus to say, okay, this is what my system is supposed to do, and have some way of testing it, that sort of thing. So it makes it much easier if a lot of that burden is taken on by your distributed database. Backup and restore, I've repeated many times deliberately because I think it's just a very important problem. Upgrade. Now you have, 200 nodes. How do you upgrade your system? You're not going to stop it and upgrade every node. You want some kind of rolling upgrade system that you can sort of do it in a way that it's easy, you have full uptime. That should also be part of your database's capabilities. That's one of the other very important dimensions. So, how does TiDB do it? So, most people would be familiar, but the ones who aren't, I'll just quickly go over this because I'm running out of time a bit. So it has this thing called PD, so you can have, which is the placement driver, it's the metadata server. We'll ignore Flash for now. You have the storage nodes, and TiDB divides the data into chunks and sort of spreads them out so that if one of them goes down, you can read it from the other. And this, because this is an HTAP conference, so the OLTP and OLAP is what the HTAP thing is. And one important thing that I tell everybody, TiDB optimizer can even take a subquery, and if it makes more sense to send it to column store, it'll send that fragment to the column store, and whatever it needs from the row store, which is TiKV, it can do that and then combine the results, which I think no other database or HTAP, anyone who claims HTAP has. It's a very powerful thing. Also, this is fully consistent. The TiFlash, it uses Raft, whatever it is, like a non-voting member, I forget what it's called. And it's fault tolerant across AZ. And the last one is the one that's about analyze table and create index. It's called our distributed execution framework. I'll get to that in a slide later. So TiDB does not compromise on availability. That's the key. This is non-negotiable. So it'll say, okay, fine. Availability is number one. So it's a highly available, geo-distributed, and replicas can be across different regions for many things. It leverages Raft. PD will automatically adjust the placement of the regions to optimize performance. Having said that, there is also an interface as part of its SQL interface where you can manually move things around. If you know what you're doing, you can do that too. So while it's the default is automatic, but you can have, you can manually set the rules for placing the regions. So it has the flexibility. It has resource control, which I won't go into right now. So it has a disaggregated architecture, so which means that compute, which is the front end, is separate from the storage, which is TiKV. And this allows them to scale independently. So let's say your data is not growing so fast, but your connections are going very fast, you can add more compute nodes. Your data is growing very fast, but your connections or users are not growing that fast, you can scale your TiDB independently. So that's essentially the advantage of that. Also, it uses query pushdown. So that most of the queries as close to the metal as possible rather to reduce network traffic. So that's the other thing it does to reduce internode communication. Okay, where are we? Hey, this is not working. Oh, finally. So we've gone over the failover mechanism. It has automatic failover, region recovery, disaster recovery, scalable backup. So you need these things from your database if you want to scale, so that it's easier for you to deploy and manage. That is the key takeaway from this. It reduces your cognitive burden, reduces your cost in maintaining all this stuff. So what does the distributed execution framework do? It apportions and control resources efficiently at the cluster level to reduce impact on, that's its main mission. So reduces operational complexity, it lowers the risk because it also handles partial failure, it's restartable, it has a unified scheduling, and it can completely isolate your background tasks from your foreground tasks. That is, it's like one of the main things. So it doesn't affect your foreground tasks. And you can start up dedicated storage and nodes, for example, or compute nodes for doing the sorting for the intermediate files and for doing the actual sorting in memory. So you can start up those nodes, do your whole create index or whatever it is, and then you can throw those nodes away. So some interesting results. So given that TiDB cluster, 14 nodes of TiDB and 20 TiKV, 40 terabyte create index takes about 1 hour from 14 hours. And so if you do one of these, you're doing 4 add indexes an hour and a half. I mean, this is incredible stuff. I want to see numbers. On Twitter and LinkedIn, I've asked people to give me their numbers on these data sets. I haven't seen any number from anybody else. I think this is unique to TiDB. At least I'm not aware. If anybody is aware, I'm quite happy to sort of increase my knowledge. Okay, anyway, thank you.